All right, we're working real quick. Your warm-up today. What's the inverse tangent of 30 radians? 1.537. Very good, which is really close to pi halves, right? Okay, good. Yay. That was the last problem we did in the previous class, pre-cal. They're one section away from starting trig identities and trig proofs. Oh, boy. You might want to adopt the pre-cal student here starting next week. Help them through it. Okay, parametric and vector accumulation. That just means that instead of taking the derivative, we're going to be integrating. Okay, integration is accumulation. So, particle motion. We're going to revisit it parametrically, which is also kind of in vectors as well. So if a particle moves along a smooth curve in the xy plane at any time, then its displacement, which remember is its net change, is going to be given as a vector. It's the integral of the component velocity. So that's similar to what we did back in the day with linear. If we integrate from a to b of the velocity function, we get displacement, which is net change, right? Positive and negative would cancel. Whereas if we integrate the speed function, which is the absolute value, we saw that yesterday or 2 days ago, we get the distance traveled. And they're only the same if the velocity function is positive. So with two equations, one for horizontal, one for vertical, we're going to do the same thing. We're going to integrate the component velocity equations, x prime and y prime, and we're going to list the displacement as a vector. Okay, so not as a single unit. Total distance traveled we express as a single unit. That's the arc length. Displacement we express as a vector. Okay? So then we can add to that, if you want to know where you are at any given time, remember it's a function of two things. It's where you started plus your displacement. So if we add to these two values here in vector form, the initial position of the x and the initial position of the y, we will get the position vector, okay? We'll know exactly where we are. And of course, just to review what we did the other day, if you want the total distance traveled, then you don't want things to cancel. It's the integral of the norm or the integral of the magnitude of the speed or the velocity, which is the speed, and we get that right there, which is the arc length. Okay, so again, if you finished 7.1, you kind of already did this. I want to go through some calculator etiquette today, though, because now sometimes we might be in parametric mode, and sometimes we might want to go back to rectangular mode. So if you want to come up here and grab a calculator, go ahead and do that so that you can follow along. And while you're doing that, I'll make this note right here. To see curves or integrate parametric equations, comma, you can stay in parametric mode. All right, so since y'all are seated again, we might want to switch back from parametric mode to rectangular mode, or function mode as your calculator calls it. But if you want to see the curve and you have the calculator, you can graph an x1 and y1. You can hit graph and see what the curve looks like. That's fine. You can even integrate. You could set up your integrals in parametric mode. That's fine. But when you're trying to solve an equation, you probably want to be in function mode. Or that's what your calculator calls it, or what we've been calling rectangular mode. That's one of the three things that you're going to be expected to do on your calculator. Solve equations. Okay? The other two being integration numerically and derivatives numerically. So I'll show you what I mean by that as we go through this section. So this is a calculator primitive question. An object is moving along a curve in the xy plane. So if it says curve or xy plane and you have particle motion, you know it's a parametric / vector. It has position, x sub t, y sub t at time t. And notice we are given the derivative equations. So these are the velocity components. At time 2, the object is at the point 1, 4. So that means that when t is 2, x is 1, bless you, and when t is 2, y is 4. part A, first of all, find the acceleration vector at t equals 2. Now, because this is a calculator question, I am going to show you how to do it exclusively on the calculator with the right notation to get full credit if this were a free response question. All right, so the acceleration vector at 2, how do I get acceleration from velocity? Derivative, right? So dx dt is the same as x prime of t. And you can refer to it as x prime of t or y prime of t similarly for dy dt without having to label it. You don't have to relabel dx dt x prime of t. It's understood, okay? So here's what I'm going to do. To show my work, I'm just going to say acceleration. Oops, that should be an A, not a sigma. The acceleration vector at 2 is, and I need to show what it is I'm typing into my calculator. I'm going to say x double prime of 2, comma, y double prime of 2. Does that indicate what I'm doing? If you look at that and you saw x double prime of 2, you would know that I'm taking the derivative of x prime and plugging in a 2, right? That's all you need to show, okay? Or, if you want to keep it in Leibniz notation, you would say d squared x over dt squared, evaluated at t equals 2, comma, d squared y over dx squared, evaluated at t equals 2. Bless you. Yeah. That's another way to do it, but that's a lot more writing. So it doesn't hurt to call dx dt x prime of t, but if you forgot to do that, that would be fine. They are understood to be the same. So here's what I'm going to do now. I'm going to go to my calculator and make sure I'm in radian parametric. There's radian. Parametric is PAR for most of y'all. And when I go to y equals now, I'm going to type in my first derivative equations. Okay? So I'm going to put t sine of t. That is my x prime, but I'm putting in an x. So you got to be careful. It's not position, it's velocity. And in the second one, I'm going to put cosine of t squared. And I'm squaring it before I close the parentheses. That's important because that squares the angle and not the entire cosine function. Now, I don't really care what the graph looks like. I just want to refer back to that. So now second mode gets to the home screen and then flush by tangent, inverse to 30. And now all I got to do is type in my calculator what I've already indicated on my paper/iPad. So how do I take the derivative on the calculator numerically? Math what? Math 8, right? Math 8 is n derivative. So you hit Math 8, and I'm going to take the derivative, first of all, of the x prime. So the derivative with respect to, if you hit x, you're going to get a t. That's fine. We're in parametric mode. Now, how do you recall your function? It's the same thing we've done. Alpha trace. If you hit alpha trace now, you don't get y1, y2, y3. We're in parametric mode, so you get x1, y1, x2, y2. So it's neat. You can still refer back to your y equals menu. I want to take the derivative of what I have in x1, which is actually my x prime, and I'm going to evaluate it at 2. So I'll hit enter. And now I'm just going to write that down to 3 decimals, 0.077, comma, and then I'll do the same thing for y prime. So alpha, I'm sorry, we're not ready for that. Math 8, again, with respect to t. This time I'm recalling alpha trace. I'm recalling what's in y1. That is number 2. So go down and select it and hit enter, and it's still with at t equals 2. And I get 3.027. So that's all the work you would have to show, and you could get full credit for it. Now, could you do it by hand? Sure. You could take the derivative of t sine of t using the product rule, and then plug in a 2 to that expression and show the work here. And you could take the derivative of cosine of t squared, and then plug in a 2. But when you do that, number one, it takes a little bit longer. And number two, you might what? Mess up. You might make a careless mistake. So there's a difference between, calculated problems and non-calculated. Use the calculator to your advantage. But anytime you have a calculator, you have to indicate exactly what it is you're typing into your calculator to get that answer. Okay? All right, so I'm done with that. If I anticipated that I might have to reuse those numbers, let's say I was finding the velocity vector, which would be an ordered pair, I might store this as A when I found it and store that as B when I found it, so that when I find the speed, I could recall them. Okay, but we'll come across that bridge when we get there, or we'll cross it when we get there. Of course, we'll come across it when we get there, unless we don't see it. All right, letter B. Write an equation for the tangent line when t equals 2. So this is kind of review of 7.1. What do we need? We need a point and a slope. Okay, and this is at t equals, what did it say? At t equals 2. All right, so first of all, what is the point when t equals 2? 1, 4. They didn't give us the equation, but they gave us the point, so the point is 1, 4. So, like Bon Jovi says, we're halfway there, right? And then it's National Sing Out Loud Day, so, oh, living on a prayer. Very good. You know, if you go to see Bon Jovi, he's on tour right now. He can't even hit that high note anymore. He goes, oh, we're halfway there. And then he holds the microphone to the audience every time so they can go, oh, and try to hit that high note. Living on a prayer. So, huh? He's not 80 years old. He's like 55, 56, 54, maybe somewhere in there. Keith Richards is like 280 years old. Yeah. But you know what? Bon Jovi on tour right now, he's touring without Richie Sambora. So it's not really Bon Jovi. It's like going to see the Rolling Stones without Keith Richards, or Guns N' Roses without Slash, or Bon Jovi without Richie Sambora. Okay? Anyway, I forgot what we were doing. Oh, yeah, we're finding slope. So we need the derivative at 2. So here's what I'm going to show. I'm going to show this is going to be dy dx at t equals 2, which is just y prime of 2 over x prime of 2. Is that right? And they gave us x prime and y prime. So now on my calculator, here's what I'll do. From my home screen, I'm going to take the quotient. Alpha y equals gives me my horizontal division bar. I now want to evaluate y prime at 2. So I'm going to recall it alpha trace number what? 2. Remember, it's showing up as y, but that's really y prime. And then if I open parentheses, put in a 2, that's good. And then scroll down, do the same thing, alpha trace, recall what's in number 1, evaluated at 2. And I've already written that down on my paper. And so now I can just hit enter, and I get negative 0.359. And again, if you think that you might need to use that number ever again, store it. Call it C. We've already used possibly A and B. Call it C, store it as C. But that's a 3 decimal thing, so I think we're ready to answer the question now. So, L of x, I'll just get in the habit now of calling the tangent line L of x. It's going to be the y value of 4 plus the slope, which is minus 0.359 times x minus 1. So notice I haven't plugged anything in. Actually, I could have literally have just called the slope if I wanted to. I could have called it cosine of 4 over 2 sine of 2. You could have done that. Cosine of 4 over 2 sine of 2. That would be just plugging in a 2 here. So that works also. All right, part C, find the speed of the object at 2. How do we find speed? Is it a vector or a single quantity? Single quantity, right? That's the Pythagorean theorem. So the speed is going to be the hypotenuse length. So it's the square root of the x prime of 2 squared plus the y prime of 2 squared. Now let's do this one 2 ways. It is a calculator question, but you don't really even have to use your calculator. So because they gave you x prime and y prime, you could just say when you plug in a 2 for x prime, you get 2 sine of 2, and you can square it, plus the y prime, since they gave you y prime, just plug in your 2, and you get cosine of 4, and you square it. All right, so, what's that? Oh, yeah, 2 sine of 2, not t. Thank you. Yeah, my bad. 2 sine of 2 squared. So that would also work. Just because it's a calculator question doesn't mean you have to use your calculator, and you don't have to simplify necessarily. So that's probably a faster way to do it, but you could also do it this way, right? If it's a multiple choice question, they're probably going to have the answers as a decimal. So let's do it that way too. second x squared gives you your radical. Now x prime squared, my x prime is in x. So alpha trace 1, and then open parentheses, plug in a 2, close parentheses. If you square it like that, that squares the quantity. Plus, again, alpha trace number 2, evaluate it at 2, close it and square the quantity, and you get that number right there, which the 3 decimals is 932, 1.932. So you can verify if you want that the exact value on the left is equal to that decimal value. So either way, you're using your calculator and you're putting down the right notation and letting your calculator do pretty much all the heavy lifting for you. All right, last 3. Oh boy, this is a long one. Okay. Find the displacement of the object from 2 to 7. Displacement. Is that going to be a single expression or a vector? That's a vector. Okay, so here's what we want to do. I'm going to label it displacement, and it's going to be the integral from 2 to 7 of x prime of t, dt, comma, the integral from 2 to 7 of y prime of t, dt. It's a little bit easier, again, to use function notation than it is to use Leibniz notation in this case. Do you think we need to show anything else other than that? We don't. And again, notice I'm using x prime every time instead of writing down 2 sine of t, which you're more than welcome to do. It's just a lot faster, a lot easier. And now we pretty much have our template. That's what we need to do. So we have 2 calculations. So now how do we do numeric integrals from the home screen? Math 9. Yeah, so math 9 from 2 to 7. Our first equation, x prime, alpha trace, is in 1. And with respect to x, which when we hit it is t. That's fine. At this point, we want to be in parametric mode because we want to refer to our parametric equations. So that's negative 6.361. And then we do very similarly the integral from 2 to 7. So I'll just go back and recall it. Delete that, and now alpha trace number 2. And we get 0.096. So the particle ended up on that 5, if you wanted to let t be seconds, on the 5-second interval from 2 to 7, the particle ended up a little bit more than 6 units to the left of where it started and just a smidgen above where it started. Now that doesn't mean it was traveling left the whole time and up the whole time. It could have been zigzagging, darting around the whole plane. But in the end, it ended up 6 units to the left and very, very, very slightly above where it started. Okay, part E. Find the distance traveled from 2 to 7. Distance traveled, is that another vector or is that a single quantity? That, in parametrics, is a single quantity, and it's also known as the what? Arc length. Yeah. So here we go. I'll call it distance here, D-I-S-T, as opposed to displacement. It's the integral then from 2 to 7. And again, all we have to do is show our setup. It's going to be x prime of t now, the function, squared, plus y prime of t, the function, squared, dt. And again, make sure your radical covers the last little square, but not the dt, and make sure your dt is there. That's all you have to do. That's your setup. You don't have to write the actual functions for x prime in there. So now we go back to the home screen, math 9, from 2 to 7. And the radical acts as the parentheses, so we'll put square root. Okay, x prime, remember for us, is just x. That's in 1. And then you square it. So here's the really nice thing about having your function in y1, y2, or whatever it is. When you square the function, you don't have to worry about having parentheses around terms or factors. You just square the function's name, and it squares the whole thing. Plus, similarly, alpha trace number 2, we'll square that. And, of course, it's with respect to this. Oops, you got to make sure you click outside with respect to t. So just quickly double check, triple check. Notice it's missing the primes here, so that's the one thing that's a little bit kind of awkward. But remember, we put our primes in x1, so it's good. Hit enter, and we get 0.13. Woo! Okay, it took a little while. 13.229. So in netting 6 units to the left and a smidgen above where it started, it traveled through 13.229 units of length. Man, is there anything left to do on this problem? Yeah. Where is it at 1? We want to know its coordinates, its position. So now we want to say, okay, it's a function of where it started plus where it ended up. So let's go ahead and write it out here. The position is going to equal, you can write it as an ordered pair or a vector. What was the starting x value at 1? Well, let's come all the way back up here. Do we know? Hang on. Yeah. Let me think about this here. Where was it at 1? I think I meant to make this a 2. We don't know what the position was at 2. We don't know the starting position at 1. Sorry. So make that a 2. That's what I meant to do. All right. So there you go. This is referring back to the initial ordered pair. I just need to change the notes. So at t equals 2, what was the starting x value? 1. Okay, so that's what we want to do. So now it's going to be 1 plus, and then your displacement, which is going to be the integral from, hang on, my bad. I'm getting tunnel vision here. I'm not seeing the whole story here. I want to find actually where it is at 1. We know where it is at 2. Yeah, so let me come back up here so I can see it. Okay, there we go. So here's the initial information. Here's your starting x. Here's your starting y. And that corresponds to 2. Okay, I got it now. Thank you, guys. So now the position is going to equal, we got this, the starting position. Now remember, it doesn't really matter what the starting position is. It doesn't have to correspond to 0. It's just whatever you're given. We have information at 2, so the starting x value is 1, and then plus the integral from when we were at 1, which was 2, to where we're trying to get to 1 of x prime. So we are integrating backwards here, aren't we? Which is fine. It's kind of like we're detectives going back in time. Comma, same thing. At t equals 1, the starting y value is 4, and now we want to find the displacement from when we were at 4, which corresponds to 1, to where we're, 2, I get it, 2 to where we're trying to get 1 of y prime of t dt. There we go. You might want to do this too if it helps. You could say it's the point 2, 1, so that's your t comma x. And then it's the point 2 comma 4, which is your t comma y. If you need to do that. That might have helped me here. It looks like I'm kind of struggling with this. But essentially, it's everything we've done before. We're just doing it twice. Okay, so now that we have our setup, and that's all you'd have to show, let's go to the calculator. Flush. Okay, clear it out. 1 plus math, what for the integral? 9, going from 2 to 1 of x prime, which for us is in x sub 1, which is 1 with respect to t. Hit enter. Write it down to 3 decimal places. Negative 0.44. Do we need that last 0? Yes. It's not terminating, so we need it. And then very similarly here, 4 plus math 9, the integral from 2 to 1, of y prime, which for us is in y sub 1, so alpha trace number 2, and then with respect to t. 4.443. So again, remember, if we don't add the 1 or the 4, we're just finding the displacement from 2 to 1. We have to add the initial values to get the actual location. Okay, there you go. The good news is when you actually take these tests, you probably won't have that many questions, but they could ask you pretty much any of those questions, and you have it on a sheet of paper, so your eyeballs can just drift up and down. You do get the tunnel vision on the iPad, so it does kind of fluster you sometimes. All right, but we got it. Any comments or questions on that one? Anybody know any good singing jokes in honor of National Sing Out Loud Day? Yes. Oh, somebody first period didn't have one, but they made one up. This is kind of how we got to thinking about Bon Jovi. They said, why does Bon Jovi go to church? And I said, I don't know. Is it because that's where his wife goes and she takes him? He said, no, he's living on a prayer. And I was like, oh, okay. I was halfway there, and then you got me the rest of the way by telling me the punchline. He made that up. I thought it was pretty good. And then I said, you know what? That song that you just referenced in your punchline, that's one of the ones where a lot of people sing out loud. And we've already had that conversation, so we won't do that again. So now, Gorell, you've had time to think of a singing joke. Oh, you haven't? Okay, all right. Well, let's move on to example 2 then, shall we? Any junior girls sneak in during example 1? Okay. An object moves along a curve in the xy plane. It has positions, blah, blah, blah. T is greater than or equal to 0. That's good to know. And once again, we're given dx dt, which is the horizontal velocity. But then, where's dy dt? It actually says the derivative dy dt is not explicitly given. Like, here's your freaking dy dt. Is that what it means? Explicitly given? No, it just means it's not stated. It's not there. At time equals 2, the object is at 3, 5. Okay, so there's another initial condition. We know what the initial x and y are. And initial just means at 2, not at 0. Part A, find the x-coordinate of the position of the object at 4. So this is kind of like the last thing that we just did on the previous problem, but we're only doing it for the one coordinate. So at 4, we'll just say x of 4. It's equal to, now I'll go ahead and write out the notation here. It's going to be our starting position, which is x of 2, plus the net accumulation from 2 to 4 of x prime of t dt. Are you all okay with that? Okay, good. So that would be all you'd have to write, believe it or not, if this were a calculator question. But is this a calculator question? No. So in order to help ourselves evaluate it by hand, let's go ahead and plug in the actual values. X of 2 is 3. I'm actually starting at an x value of 3, plus the integral from 2 to 4 of x prime, which is 2 sine of t squared. Boy, oh boy, oh boy. So now I'm looking at that, and I'm like, okay, if this is a non-calculator question, I'm going to have to be able to find the antiderivative of sine of t squared. Do we know how to do that? The inside function would be t squared, and its derivative is 2t. Yeah. Good question. Power reducing identity would work well if it were sine squared of t, not sine of t squared. We're squaring the angle, not the function. So what I think on this one, I think this one is a misprint. I think this one is supposed to involve a calculator. Yeah. My notes and my worksheets evolve every single year, and when we start getting this deep in the air, I start going faster, and so there's more and more little careless things. So I'll fix this for next year's group. But this is a calculator question. So it's nice that we didn't know that at first, because if it is a calculator question, you have to show either one of these or both, okay? But for sure you need to show either one of those. So let's go ahead and go to the calculator. And do you want to put your dx dt and y1 or x1 again? No. You don't need to? Well, it's a multiple question problem. So if it were like a standalone multiple choice question, I would say don't bother putting it into x of 1. But if it's part of a free response question, you might need to refer back to it. So I'm going to go ahead and put it in x1. So it's 2 sine of t squared. And you know what I might also do on my paper then at this point? I might just come over here and just call that x of 1. Because that's where I put it. We remembered that on the previous problem, so you don't have to do that here. And now I can just type this in. So from the home screen, here we go, 3 plus math 9 from 2 to 4. And I can type in 2 sine squared of t squared, or I can just refer to it now, alpha trace number 1 with respect to t. So it saves a little bit of time there. Bless you. You're welcome. 2.884. Okay, 884. Are there any units there, like meters or feet? No, there's not. All right, letter B. At t equals 2. Hey, what else do we know about t equals 2? We know it's at the point 3,5. Sweet. I'll just write that there to try to avoid tunnel vision. The value of dy dt is -6. All right. They didn't give us the explicit equation for dy dt, but we do have a breadcrumb, right? We have a little piece of information. At 2, it's -6. Neat. Write an equation for the tangent line at the point x sub 2, y sub 2. Okay, what do we need for the equation of a tangent line? Point and the slope. Do we have the point? Yeah, x sub 2 is 3, y sub 2 is 5. I knew that because I brought it down from the top. But on the actual test, you could just do this with your eyes. Okay? Just roll them up. Or even tilt your head. You don't have to scroll or do anything. We do need the derivative now. Here we go. So using correct notation, dy dx at t equals 2. That's y prime of 2 over x prime of 2. Y prime of 2 over x prime of 2. What is y prime of 2? -6. They give that to me. Sweet. How do I find x prime of 2? Plug it in there. So I'm not going to use the decimal version. I could easily go to the calculator and find it, but I'm just going to call it 2 sine of 4. Yeah, 2 sine of 4. So again, even on a calculator question, you can leave exact answers. So that's my slope. So here we go. The equation L, I'll put so, there you go. L of x is the y value of 5 plus the slope, which is actually minus because it's a negative number. Can we simplify that? Sure. Do you want to? No. Yeah. Are you going to be able to sleep at night if we don't? You can? All right. So you leave it as 6/2. I'm going to call it 1/3. I just lost my check, right? Yeah, I did that one on purpose. Yeah. Yeah, so be careful. If you do simplify something that's correct to something that's incorrect, you lose the point that you had already had. So yeah, just be careful if you do that. But I'll call it 3 over sine of 4. That's fine. It would also be acceptable to have a 3 decimal approximation of the slope at that point. Right, Gridley? Yeah, okay, good. Part C, find the magnitude of the velocity vector. What is another name for the magnitude of the velocity vector? No, the magnitude of the velocity vector. Yeah, we have a vector like this. It's velocity. It has a direction, which remember is that away, and it has a length. The length of the vector is the magnitude of the vector. It's called the norm of the vector, and it does represent the speed. Okay, so they might ask you to find that in any number of ways. Find the length, find the magnitude, find the norm, or just find the speed at t equals 2. All right, so here we go. The speed, I'll go ahead and label it. The speed is equal to, it's just a Pythagorean theorem, right? Just the potato theorem. That's a different theorem. Potato theorem. That's x prime of 2 quantity squared plus y prime of 2 quantity squared. If we integrated that without the 2, but instead with the t's, that would be the arc length. So they are kind of related. All right, so can we just stop there? Is that a numeric answer? No. So what is x prime of 2? Well, we just found that appear to be 2 sine of 4. So even with the calculator, you're welcome to pick it up and evaluate it. But I'll leave it as 2 sine of 4, the quantity squared, plus y prime of 2. Where am I supposed to get that? Again, they still gave that to us. So that is -6 quantity squared. Now feel free to write that as plus 36. That's fine too. Can I stop there on a calculator question? Yes, you can. That's a numeric answer. Not very satisfying or gratifying or rewarding, but it is correct and it is exact. So stop there. Parentheses are important. What if I didn't put parentheses around that and I called it 2 sine of 4 squared? Now it's wrong. Just say it's wrong. They might, no, they might not. They will count it wrong. Yeah. Okay. Now you are welcome as you write it down. You can simplify. You can say, 2 squared is 4, and that's sine squared of 4 in the condensed notation plus 36. That's fine. You could do that. How many bonus points do you get for that? None. 0, right? Or as they like to say at the reading, they'll give you 0.4 bonus points, but then they always round down. Always round down. Okay. It makes them feel better that way. We gave them a little bit, but then we had to take it away. So like if you ever work parallel solutions, you like work two solutions to the same problem because you're not sure which one's right, that's what they'll do. They'll grade both of them independently, average the score, and then round down. Always round down. So if you had like 0.9 average, they would give you 0 points. Okay? Just FYI. So don't give dual parallel solutions. Okay, go with one answer and go with it confidently. And don't scratch anything out either unless you have the intention and time to replace it with something. Because remember, on a free response, something is better than nothing. Same thing on the multiple choice. You don't leave anything blank. They don't penalize you anymore for wrong answers. You accumulate points. All right. Part D. For t greater than or equal to 3, so from 3 and in the future of 3, the tangent line to the curve has a slope of 2d minus 1. I can label that right now then as what? Just to kind of help myself with notation. dy dx, fantastico. So dy dx is 2t minus 1. Find the acceleration vector at 4. All right, so begin with the end in mind. If you know where you're trying to go, you can work backwards from there. So I'm trying to find the acceleration vector at 4. So I'm trying to find a vector at 4. I know from experience that that's going to be the derivative of velocity, but I don't have the velocity vector, so I'll just call it x double prime vector of 4, comma, y double prime vector of 4. Yeah? Okay, so now if I can work on finding those independently, I'll have it. So how am I going to find x double prime of 4? Well, they gave me the equation way up here for x prime. So I just need to find its derivative and evaluate it at what? 4. Do you want to take the derivative by hand? It's going to be 4t sine of cosine of t squared. See, I almost messed up. So it's up to you. If you want to take the derivative by hand, chain rule, and then plug in a 4, that's great. I'm not going to trust myself. I already have it written on my paper as x double prime of 4. So I'm just going to go to my calculator, math 8, the derivative with respect to t of alpha trace. Where is my x prime? It's in 1. So that's going to give me the second derivative, right? The derivative of x prime, and that's evaluated at 4. I'll hit enter, and I'm writing that down, negative 15.322. Okay, and it's entirely up to you if you'd rather do it exactly. All right, so now the fun part. Not that we haven't been having fun, I'm sorry. I need to find y double prime of 4, but they did not explicitly give me the equation of y prime. So how am I supposed to find y prime of 4? Oh, yeah, this is probably going to come into play, right? Why else did they give it to me? So let's think about it. dy dx, we know dy dx in general is y prime of t over x prime of t. Yes, yes? All right. Let's plug in what we know then. dy dx is 2t minus 1. They told us that, right? Which, bless you, equals y prime of t over, do we know what x prime of t is? Yeah, it's 2 sine of t squared. Sweet. So that's 2 sine of t squared. Can I now solve for y prime? If I look at this equation, I certainly can. I multiply both sides by 2 sine of t squared, and I get 2t minus 1 times 2 sine of the quantity t squared, close, and that equals y prime of t. I found an equation for y prime of t. Go me. So now I want to find the second derivative at 4. Well, I don't need to find it there and then rewrite it. I can, but because I have y prime there listed as a function, I can just now go to my calculator and hit math 8, the derivative with respect to t. I have nothing for y prime typed in, anything in y1 or x1, so I'm just going to type it in, parentheses, 2t minus 1, close, and then open. I'm going to type it just like I see it on my paper, 2 sine of, it opened it, so t squared, close it for t squared, close it for 2 sine of t, and then with respect to, or at, 4. Double check, triple check, make sure it's in there correctly. How does it look? As y'all are my witness. Okay, good. So, wow! Negative 108.408. 0.408. Now, how did I know that that was working? Because I was finding it at 4, and they told me that dy dx was good for all values greater than or equal to 3. So I knew that worked. All right. So that's a pretty cool thing to do right there. And that's a pretty common thread throughout a lot of these free responses. Knowing that dy dx is y prime of t over x prime of t, you're going to be able to set up equations like this and either find other equations in terms of variables or values. If they had given you numeric values, you could find other values that way. So very important idea there. All right, and that, believe it or not, concludes everything we need to know really about 7.2. Yeah, integration, because we did some of that on the worksheet for 7.1. So last chance to get anything on the recording. Anything? Any warning words of wisdom for the people at home watching this? Those two people, which is probably the same person watching it twice. Pay attention better the first time. Is that what you want to tell them? Okay.